process created by a swarm of drums. This process merges design and production within a singular process based on behavioral robotic systems and a composite material, which is a rapid phase-changing cured by UV rays or natural sunlight. We're trying to produce a bridging structure utilizing minimum amounts of materials. In contrast to conventional construction techniques, our system harnesses strong techniques in order to propose a construction process that can be pre-designed yet allow for flexibility in order to be implemented within a variety of environments through real-time structure feedback. To some extent, model and drawings are not the final tools for prefiguring what is to be built. Form and structure are more flexible with construction environment, material behaviors, etc. The construction of lightweight cantilever and bridge structure in hard-to-access locations is made possible in responding to the intricacies of complex size condition spaces difficult to construct within, such as the high spaces between buildings, mountains, and cliffs, become territories for further architecture development. The construction in this scenario arises from the printing sequences of swarm drums and their responses to the real-time structure analysis. The construction process alleviates the need for scaffolding in what is often a complex and awkward site-specific location while producing designs that are structurally and therefore materially efficient. The research argued for a time-based system adaptive process that is flexible in materialization, form, structure, scale, and configuration that is capable of responding to fluctuation in local environments and weather, structure, and material behavior and other unpredictable site constraints. We choose the drones from Crazy Fly to helicopter because the main benefits we can get from the helicopter is it has relatively high payload, which are around 4 liters, which can make our touch with the containers and the resin and the 3D printing hardware possible. We use the helicopters to test the basic movement like circles, curves, straight lines, and positioning movement on helicopters using optic-track camera system and get the real-time position data, which means controlling multiple copters flying in sequence is possible. We also test this positioning outdoor and to see how it behaves so it can achieve the task on time. We also made a rough measurements about the helicopter hovering, which from 4 to 10 centimeters in different directions in gentle breeze and day. While we test in indoor is quite stable. So we can utilize these different movements and this to our design. We can use our real-time structure analysis to see the movement of the drones feedback into the design of final geometry development. This sensor touch with Quasify just tests how we get the data from small quadcopters, and then we using this data to do some avoidance movement. About the basic cantilever bridge research, we talk with the AKT to get the safety value proportion of cantilever is 1 in vertical depth in cross section 2 to 7 in the whole length, and the minimum angle of support is around the best minimum angle of support is around 25 to 30 degree, and we also transform the tube into arch to find that tension decrease a lot and the compression also decrease. This diagram just shows how we connect the cantilever into a bridge, and it shows the biggest stress value decrease a lot in two sides, but the stress in the middle area of the bridge increase. So the results let us think about the way of bridge construction is the typical traditional method to build a bridge. It will add a lot of support before it connect. So in our system, we thinking about the architecture, only considering the data load of the structure and make sure the construction sequence safe. After it's become a bridge, we consider the life load because the material is light, so we can add a lot of materials. This is just showing the stress, showing that when the cantilever connect, it will change the whole geometry stress direction, so we can add the materials more in the meter by the quadcopters. Serious 3D pen models just showing how we understanding the cantilever and the bridge structure development and the material organization. This is a section of different tube-like. So we're thinking about the lightless curing tan, and it's easily attachable with the drum. So we from the clay and the resin, and the science, sawdust with the resin. To choose the right material is the resin using curing by just a simple tool and pouring liquid resin, so it can instantly solid. This is the detailed pattern of this cantilever structure. And this model just showing the potential of this material can be connect together and can be cantilever. This is showing increased scale. We're thinking about using the circular wave aggregation to make the section. And we are adding different angles to support together to get just the best angles, or is better up or down. But this result just shows us we need to think about the base, how the resin connect with another vertical surface. In this video, it just shows we increase the size of the tube, and we have junction touch with the base, so make it stronger.
As far as printing hardware systems are concerned, we use UV curable resin as our printing material. The principle of using of the systems is to turn the liquid stages of material into the solid one instantly. Using UV curable resin to using UV laser beam to solidify liquid resin when the material is dripping down in the air. The system have been developed into 5 versions. We start from the first prototype. The logic of making the prototype is quite straightforward, using 4 laser diodes, focusing on the tip of the nozzle to kill the resin, using a peristaltic pump to distribute the resin from the container to the nozzle. After testing the first prototype, we found that some problems need to be fixed in the next step. For instance, the intersection point of the laser beam was not correct. The speed of the resin was not adjustable. The adjustments of the of the arms are limited, and the diameter of the tube was too small. So that we start developing the second prototype, adding a motor speed control to find the best speed for printing, improving the arm to be more adjustable. The result of the printing result was quite satisfying. However, we found that a small amount of unkilled resin drips down on the floor. So the third system is designed for attaching on a quadcopter, concerning the overall weight of the system to be in the center of the quadcopter. Adding more nozzles to get bigger cross-section of printing, attaching a sensor in the front part of the system. The sensor acts as a switch to allow the system prints autonomously. This video is showing how the sensor works. The sensor is able to detect the existing printed material ahead. Whenever there is a certain distance between the sensor and the existing printed material, the pump and the laser diodes will be turned on, printing material autonomously. After testing the experiment, we found that we still need to solve the unkilled resin dripping down on the floor, as well as there was a problem of different liquid pressure in each nozzle. Therefore, a tray is then attached on the fourth prototype below the nozzle to recycle the dripping resin back to the container, as well as we were trying to reduce the overall weight of the system. We could get bigger cross-section by using this prototype. However, the liquid pressure in each nozzle was not controllable. And finally, we developed the final prototype concerning all of the problems. concerning all of the problems that we had before, this animation is demonstrating how the final prototype is being attached on a quadcopter. And it is the experiment. The video is showing how the final prototype is printing, making long cantilever structure out of a wall. And this video, we also try attaching the printing system on a quadcopter in order to check the balance of the overall systems.
Based on the research of the flight, we developed an algorithm to simulate the flight behavior and the printing arrangement. We create a grid workspace which drones operate in, and set the drones in 3 states of go charging, job assigned, printing, fitting in rules such as drone avoidance, obstacle avoidance, printing job arrangement and assignment, fighting nearest charging and printing, printed job check and the printing sequence arrangement and so on. And we test this algorithm in printing a very basic of geometry, which is a dome. In this simulation, different color of the drone represent different states. And the red circle represent the drones detect obstacles nearby in flight paths. We show the rules, all the rules in the simulation. We also evaluate this algorithm to see what's the possibility we can improve it, improve the rules. We also research about the choreography of the swarm printing to enhance the construction efficiency. A single resin cantilever printed by a drone is weak, and the swarm printing can print out an interwoven long cantilever in a shorter time. These are the simulation of 3 kinds of behavior, showing the circular swarm printing, overlap structural printing, which will greatly increase the efficiency.
So according to the choreography behavior of quadcopter, we begin to think how to use this method to print a surface. We design pattern with 2 grids overlapping with each other. It is simple but suitable for choreography, so drones can print it in sequence, and this pattern can get a lot of junctions in each corner of every small grid, which is good for the physical performance of the surface. We also consider the behavior of our material, so the 2 layers can merge together easily, and the regular grid will be changed by material behavior, so we can get a porous surface. After that, we begin to think the structure of the surface. We research bone structure because it is a high efficient and light porous structure, and we find the microstructure of bone is aligned by tension and compression. So we also use a finite element method to analyze bridge structure and try to remove the material in low material utilization area. And we find the stress in the other part are reduced. Based on these 2 research, we write an algorithm to get our porous structure. Basically, the agents will follow the direction of first and second principal stress, and they will aggregate in high stress value area and disperse in low stress area. In this simulation, we have a vector field. The red vector is first principal stress, and the blue one is second principal stress. The agent will follow the direction of local stress vector. And in this video, we can see the agent will aggregate in high stress value area and disperse in low stress area. We also run the algorithm in a large-scale bridge to get the material distribution in this bridge. And then we design our typical section. We transform the grid according to material utilization, which means in high material utilization area, we have a denser grid. The curves we get from algorithm will become the ridge, which are the mean structure to strengthen the surface. This animation shows the whole picture of a typical section. The density of grid is according to the material utilization, and we run the agent to guide the ridges. And then according to local stress value, the ridges will have different height and size. Then some sub-ridges are generated in some open area. So this is the final result. In this simulation, this animation shows how our real-size helicopter printer, real-size resin surface. The vertical and horizontal grid will be printed first, and then the ridge will be printed. At the last time, the diagonal grid will be printed to lock everything together. And there are some micro movement of drones, like rotation and avoiding collision. And this is a simulation to combine form generation logic and printing behavior to generate the form of a typical section. And this is a rendering of typical section. And this is the physical model we did. So it is clear that's how the printing method and the material behavior will change our form. After that, we investigate the safety of this construction method, because sometimes the environment factors such as wind and the inaccurate printing may get some problem. So we are proposing a real-time structure analysis, which means we can get the structure data and analyze in software. And when we found the weak point, the quadcopter will fix it. Another real-time structure analysis is, as we can see in this simulation, when the printing job is assigned to drones, software will analyze structure in advance, and the long cantilever with high stress value will be stopped, and it will wait for the others to bridge together. By doing real-time structure analysis, we can optimize the printing sequence and ensure the construction safety. So as we can see in this simulation, the cantilever at the bottom side is waiting for the others to bridge together and then be printed.
As we proposed, aerial robotic construction provides an opportunity to construct in hard-to-access and precarious locations, such as the high spaces between buildings, mountains, and the cliffs. In most of the cases, the cantilever and the bridging structure is needed, which is logistically difficult to construct and typically requires scaffolding and a large quantity of material. Inaccessible natural landscapes are difficult to construct, yet they are inhabited, such as Guoliang village, which is in China, and there are many such villages in China. People began to live there several centuries ago to avoid the war, and the only connection with the outer wall relies on the pedestrian road dug out manually alongside the cliffs. It is inconvenient, but more and more people travel there because of the beautiful natural scenery. We choose the site for the application of the aerial robotic construction. We propose a shortcut and a watch-out space for the villagers and the travelers. This video shows how we get the original form, which we can put into the algorithm to create the final geometry. Actually, we achieved this original form according to the site analysis and the basic structural analysis. So after we create this original form, we put into our simulation to create the final geometry. This simulation incorporates all the research and the rules we did before, such as the material distribution and structural growth based on the stress, the flight behavior and the arrangement also affect the printing process and the form generation. The printing sequence are decided, and the strengthening of the structure happens when the structural stress exceeds a certain range, as we can see in the screen. After the simulation, we got this got this geometry and put into random modeling, and finally we get the final project. And this shows the process construction stage. It is printed out with 360 drones at 2,000 frame time, which is nearly the 1/10 of the whole printing period. And this is nearly 2/3 of the whole printed period. And this is the final geometry. And this shows the material details and the structural form. And this is animation shows some process and some vision. We also did typical 1-to-5 model, which is a circular section, because we use this circular section in our geometry and investigate the materiality and the structural possibility. This model is built by precast resin components, and we make a metal tube as the junction with the cleave. And these are some pictures. Thanks. We can show the models.
This model is made around 5 liters resin materials, and we do the main parts by printing order and several parts by precast because we're thinking about time limitation. And we want to show this model to show this material potential. Like each component is around 1 centimeter, so in the real size is around nearly 12 centimeter. And this 3D printing model is a serious model showing how we understanding the printing sequence, like this section, how we make the section bigger, how we make different patterns to make it stronger, and how we use the frame collective structure and make this structure can standable. And that's a 3D printing model, just showing a scenario model between the cleaves. About this model is 1 to 10 typical section model. And you can see this junction. We use less material than this one. So we just use the junction, make it stand and quite stable. And this is the baby style cantilever structure. And the Raven 3D printing hardware, we're just showing the best one because the Nodder is the best that we found successfully work. And the container, you can see is black because the resin can be curing by sunlight, so it will always block the every pass. So we make it black, everything black, black to black container. Thank you.
One of the most intriguing things that you guys are doing that I think is novel and honest and so I would say innovative is that you're not claiming that the project is being produced with absolute precision. I mean, for me, that was one of the most intriguing things about the very beginning of your presentation, where you showed the variation that would occur because of wind. And so there's a kind of a drift in the kind of printing process, which I find totally intriguing. And then this kind of beginnings of this kind of mat, this kind of orthogonal mat, and then the overlay of these redundant kind of fibers for me it's just it's a really spectacular thing to see. But I love the fact that you haven't fallen into the trap of like it's got to be absolutely precise. In fact, it's so full of redundancies. The other thing for me that I find, so compelling is this idea that the drones themselves are actually sort of self-assessing. Like they're laying things down and they're actually sensing their kind of environment as they're moving through it. So in some ways they're almost building, and I wish I kind of saw this, but they're building in a way a kind of a real-time kind of 3D model somehow. And that it's somehow validating it. And so if there's a really strong wind gust, for instance, it gets blown off course, it lays a double strand where it's not supposed to be. It really can just go back and kind of compensate, let's say, for that drift. So for me, there's a lot of really, I think, intelligent kind of things that you're doing.
Yeah, I agree with everything you've been saying. I think what you've done is taken kind of the work that Tonk and Lou are doing with their shell-lace structures, but you've put so much more intelligence behind the thought process that go into it, taking into account the construction phase, taking into account all the processes, and also adding the extra elements, obviously, of the control of the copters. So it gives this really interesting organic aesthetic, which has got great structural derivation, but actually doesn't look like it in the final conclusion. It looks a lot more interesting than something that is purely derived from the structural form, taking into account the variations that you've put into your models and also the different phases of the process that's come through. So I think it's a really interesting project.
Yeah, I think I really like the final presentation. Also, not only of the product, but also the way you work with the kind of ideal type, which is as an initial conjecture about a solution, and then a series of adaptations to contingencies of the actual places where you can lock in, both programmatically and structurally, and then a series of what was all along great is the structural analysis coming in first of all after the scanning of the conditions, but then during construction. Once more, I really like that with the paralleling of the construction process being continuously scanned, being continuously verified. And then refed into the further printing process, and that this is of course demanded to some extent by the degree of contingency absorption, which is all along part of the thinking. But I really like the utilization of real time. In this case, it's not so much, I guess, stress sensors, but simply a scanning and simulation as being good enough to further project the trajectory, and then potentially having to maybe you didn't come to that point when re-strategizing rather than re-sequencing. That for me be the next point where in terms of this, once the real site locations are scanned, there is actually to some extent the re-strategizing of the design. Then when it comes to the real-time calculations being updated, it's a kind of re-sequencing, but I wonder how one could, could also be the re-strategizing of certain topological variations, of course always within a space of rules and possibilities, which need to be robust enough to capture the contingencies which you have to kind of bracket, obviously, to begin with.
Yeah, nice. I appreciate that you actually very actively, indeed, the tolerances and the issues with outside, but then the considering of the in-between stability and the true stresses, but that is very commendable. One aspect, though, is that you saw that you had to push the bridge to be kind of an arch, a compression structure. But even to get there probably, certainly since you chose a typology that goes along a long span, you need to develop quite a bit of tension indeed for your cantilever. And there, I doubt that any material you can 3D print, and certainly in the layers you're going, that it really can produce that. So perhaps one thing that you could, if you were to really take this serious and imagine to go further, is to maybe team up with the first group that we saw this today, and to include continuous tensile strands and elements that actually take the tension. And one very clear moment where this is clear, and you saw this also in your model, is that you need to connect to the foundations, right? And this needs to happen through continuous strands. And the interesting potential, certainly in how you're making this scaffolding, is that if you've seen Jan Knipper's lecture, or you've seen Archimenge's weaving kind of structure, they have these kind of hooks where they go around. And so you could start to, like you already are laying out your scaffolding, you are building these 3D very specific hooks where you can start to weave and connect all your continuous strands to. So that could actually push also what you could achieve, that you not only achieve compression structures, but that you could push it a little bit further. But anyways, even for the compression structures to get there without any formwork, which is one of your key arguments, I expect that you will need it, because no plastic will deliver you over these spans the strengths that you need. So that's a suggestion. But great work.
I also would like to follow that thinking from Philip to connect it to the first group we saw today. The idea that that you decouple the printing tool from the material carrying, and actually the string becomes a tube for the material, and that addresses another thing, a safety issue. Otis didn't invent the elevator, he invented the safety mechanism for the invention to become applied in a popular way. And this could be also here, if we think of, now you put it in a canyon, but if it's in an urban environment between skyscrapers where downwinds, turbulences are extremely relevant for flying drones, the string could also become a safety kind of tool that makes this a quite tangible strategy for densification of existing urban environments, which is a very relevant issue at the moment.
I was thinking something similar in terms of what happens if we imagine the cliffs becoming the sides of tall buildings. And Yeah, I mean, in a way to try and work around the sort of falling water paradox of this. You know, you found a beautiful natural site, and you know the one thing it needs right in the center of it is this huge object inserted that provides about a 30-second shortcut for the 12 people a year that are going to go up on the village. And the contrast is so kind of sharp that what it's making me try and think through are the ways in which this ingenious system, and it's a really kind of ingenious material system, can have work other than bridge-like or structural expectations. So for example, if it arrives in the urban setting, it could at times be thought of as circulatory or connective, but it could also be by laying out surfaces that are large enough in plan area, you would suddenly be creating platforms that could introduce programs into parts of the city that we just don't normally account for them, right? That the kinds of things that happen in large open surfaces down on the ground can suddenly happen, you know, up and down the height of this thing, and that in effect it's a far more, it could be a far broader palette of work for these things to do other than the first impulse, which seems to be let's print structure, beams, and with that a bridge. But to see that kind of range of elements as part of a much broader domain, I think is part of the discovery of the project, that in fact it could. And I think every instinct to try and first test it like that is something to back away from and say, in addition to the structural properties, what else can it do to, for example, become a means to resurface existing enclosures or envelopes? Like, you know, it's an astonishing kind of Louis Sullivan patterning technology in a way. And when you think of that role of ornament, surface, and how it gets rethought in the tall building, let's say at the end of the 19th century, at the very time in which structural engineering is brought to it, it's a really interesting kind of opening up again of that entire, and I think much broader area of discovery than just a kind of structural wizardry. And as much as that might have driven you to this point, I think you're at a great point to now, you know, go far beyond the beam-like properties to actually recall those moments in your presentation when the plates are really required, like this sort of superstructure of orthogonal lines, et cetera, that are actually just creating a completely different kind of an element than just a beam. It'd be a terrific thing to imagine of what they would do if you just cut them loose on pretty much any building on the planet, you know, to sort of rework that as material. And that it's not just about adding new material or new buildings to the city, but it's a technology that would let you, like every existing building would be your site suddenly. You know, in the sense of how tall buildings in Manhattan are used by the only birds of prey left for cliffs that are no longer in New York. You know, that for them it's just a kind of topology to reuse in a completely new way. It'd be super interesting.
Well, I think it's great work also on the side of the engineering aspect, but also on these drones. Now, you do assume, though, that they have a fairly high precision in flight. And the imprecision happens not only in the flight because of wind and environmental parameters, but also because of the sensors. For example, a sensor that detects the distance to the build structure. There's also the imprecision of the lasers. There's inconsistencies, unrobustness of the materials and the mechanisms. So what would be interesting is to include some kind of model or observation of the dynamics of the system. So you assume a perfectly hovering quadrotor platform, but you might as well assume some other platform that is not hovering or that is not a multi-rotor platform. And so how this would then influence the design perspective and the potential of these technologies.
I would like to first congratulate you for the amazing amount of work and so beautifully presented. It's very, very visually compelling. Really, really fantastic work. I am having a little bit of thoughts in relation to the 3D printing and the drones together. Maybe because of the final proposal, but it seems to me that there is a kind of a great invention on a kind of instant building material, which, and by the way, which has a lot of imprecision, but it's coupled with the computer in relation to being able to feed back some information and recalculate what needs to happen. So that part of the story is very, very well constructed. Then there is the part of the story where the drones do this and the site that is selected. And to me, for this specific site, it doesn't, yes, it's far up in the sky, and yes, it's so-called inaccessible, but actually it's totally accessible because there is no obstacles. So in a way you could have done a hanging bridge, for example, from one side to the other. So I think that the drones would need a kind of exploration of sites that are more complex, and that actually that would use really the capacity to fly in complex kind of almost forest-like sites. That I think there is some power that is not here in this site. So, if we leave the drones aside and we look at the material system, then I think the conversation for me is, well, this could also be done by hand. And because in fact the material system and all the imprecisions could be very well done by people. So in a site like this, where you begin to build a structure where you can actually climb onto and you continue to build by hand, but you are computerizing, in a way, the result of the structure you're building, and you're sending new and new information about the branches that you need to make and in which orientation and whatever. So I think that the project, I see very powerful two avenues, but that merit as they are, in a way, yeah, I think that it could evolve in two very beautiful directions. That one is to reintroduce human labor with feedback from the computer with the imprecision of human labor, and two is to use the drones in much more complex sites than this one.
That's a very nice point, and I think it's an advantage of this kind of project that aspects of it are generalizable beyond the specific decisions you made as principles, and I really like that principle of the kind of continuous feedback loop of and redirecting, and I mean Gramazio Cola and some of their studio projects have actually deliberately done that, where you combine a robot arm with manual labor, and where what is exploited by the robot is a quick positional pointing of points in space. It's an informational capacity because it's computer driven and precise, and then you use that together where there was an element of robot arm or computational robotic actor, a material set of actors, and human actors quite well, because there is a lot of things which in human actors remains superior and irreplaceable on many levels. I mean, as you personally have experienced, and all the teams must have experienced. So the dream of that total mechanization or robotization is very, very, very far away from that. And as always, will be that kind of integration of these various actors in the process.
I mean, just picking up on the comments, but I mean, in terms of my feeling about the project, I mean, I support it in all of its capacity. I think it's really important that I think we don't over-focus on the status of what we're looking at, because that is a scenario, and to be honest, they did talk about urban scenarios, but one of the things was about span, and they were, I think, very consistent about trying to look at connecting 2 points and actually doing a kind of choreography which, to be honest, is the most complex, which in a certain sense, making this almost glass sponge tubular structure and allowing it to unfold and negotiate ending points. And the reason I say that, because in particular with Rob and his studio, there has been in the past and a history of developing certain techniques that have kind of affordances that can be visualized or simulated in a certain way. But relative to the way that this project has been working on, I think that there is a really interesting hybridity of trying to create micro scaffolding systems to be able to continuously weave. And it's not a generic one. It actually allows and affords a certain strategy where this thing continuously reassesses itself, and it sort of mandates a kind of real-time repositioning, rediscovery, rearticulating, which I think is really good. Now, the issue of precision, if it's important or not, I think could open this up in very different ways. If this is a completely controlled CNC technology, using lasers and calibrating nozzles for deposition, this becomes amazingly precise, because in some way, at the end of the day, we are looking at basically drawing with light and releasing a kind of agent that actually really is petrified instantaneously. And I say that because I remember going to SciArc and thesis reviews, and Peter Testa had a project that they were using with robotic arms, and at the end of the day, even though it was an amazing research, it had a very fixed and finite idea of a petri dish and light and creating a column. And here, I think representative in some of the models and the attempts to actually scale up, you start to see the complexity actually working as a way to actually materialize this. Not to segment it in a kind of strand of resin baths, but to sort of liberate that beyond the container. And I think that's where the project for me is an amazingly important contribution to the conversation, because I think everybody can kind of make knee-jerk kind of responses to certain aspects, and they're all true. But at the same time, like when you start to see like the nozzles and the lasers being worked on by the students, and the commitment to make these models and to rethink them and to continuously refine them and to build simulation scenarios which are dynamically kind of looped back. It's not real time in terms of literal computation using real-time stuff like we saw in the morning, but it contributes to that project. And I think between the three projects in your studio, Rob, there's an interesting opportunity not to see them in isolation, and I think Philip's point was leading into that, but actually what it is that they're really contributing. And I find the instantaneousness, the drawing with light, the multi-laser kind of strategy, to actually have a kind of remote surgery in an additive manufacturing way, which I think is really important, because it's liberated from the vat, and it starts to use this kind of resin curing in a way that for sure it has material deficiencies, but it also has a promise of actually working towards a model that actually is not predicated by the finite volume of any of these kind of printing processes, and not conditioned to the ground, which basically builds this layer stratification, which we know. And I think for that, just on that level, I think it's an amazing contribution, and just want to echo that.
Yeah, I would second that. I mean, I think there's a lot of invention in the project, particularly, I mean, everything is bespoke. You know, every little behavior in the simulations has been written, as it has been in the other teams, but just, you know, every little thing is there for a reason, and it's been iterated on and worked through, and it's always been in tandem, in parallel, let's say, between what they could do with the lasers, what they could do with the resin, what they were discovering in terms of principles from structural analysis, and also what scales they imagine this material to work. Now, by all means, the materiality is not resolved, as Philippe pointed out, but it was their desire to keep it to a scale where it was relatively tangible, rather than to go into kind of printing spaces on cliffs and urban infill, which they'd actually investigated earlier in the year. And I think that was a mature decision. If we can stand back and speculate on those things now, I think it's credit to the success of where it got to, that you can now start to imagine all the other scenarios that this might operate in and how much more flexible it could be. But logistically, there's a lot of intelligence behind getting it this far that is gone incrementally. They haven't jumped through steps or fake steps. It's all been developed with a lot of rigor over quite a period of time. And yeah, I think we should emphasize that, and also that a certain maturity in understanding not only the imprecision of, you know, actually printing outside with wind and everything, and with the actual flight controllers and so forth, but also understanding that what are the opportunities with such materials and such processes of making, that things like cantilevers and bridging are not only difficult to do logistically, but they also are dynamic, and they completely invert some of the structural stress loads within the structure. So there's an understanding that a dynamic construction process can also participate in a dynamic opportunity architecture that can be in places that requires dynamics to actually make it happen. And I do agree that one could construct something else here with Martha, but I don't think that's the point of the thesis, to be so specific to the site itself. It's more about tackling the issues at this site and enables them to demonstrate. So yeah, I think that's very successful. And I just want to go over quickly the idea here that behavior is bespoke, it's specific, it's bottom up, and those behaviors are resolving structural and material concerns, logistics of the actual construction sequence, and they're also intrinsic to the character or the qualitative design results of the project. So you cannot separate something that you either like or don't like at what you look at from the way it was made and the order in which it was made. And I think that is where the studio has been really trying to address in all three projects, that sequence, material organization, and logistics are embodied and intrinsic to any qualitative design result, so that we cannot engineer out the architecture here, because the architecture is also engineered. And the architecture is expressive, it's not reductive like we see in perhaps other generations of attempting to deal with pragmatics. But here design is at the forefront, but design is playing a role as something intrinsic to also practical considerations. And I think that's something to be commended, and I think all studios aspire to these types of issues. It's not just this studio. And just the closing comment from me would be that, I mean, you can all keep talking, obviously, but it's just that I do agree with Theo's comment that actually we shouldn't be looking at this project in isolation, or Philippe's comment that actually all three projects actually were focused on very different things, and none of them have the complete picture, but if you put them all together, we start to see some exciting developments.
I want to follow up on that, because I certainly feel that maybe you have interpreted my comment as a critique, when in fact I maybe did not emphasize enough how much I like the project and how much you have done. But my comment was more meant to emphasize the fact that there is so much work that could be taken in different directions of what is here, that I mean, it's beautiful if it's true we have been presented with one side, and of course you have the time you have, and it would have been very, very interesting to present different site scenarios, because you have the flying machines, because you can address very different sites. That's maybe my comment where it was going. And also that the project could be taken in a completely different avenue of working manually and still using all the intelligence that you have developed.
Wow. Sorry. Now, just to reflect back on the meaning of aesthetic sensibilities and the aesthetic a prioris, and it's a very simple point, but it's good to reflect that at this point, that that it is beautiful in the contemporary sense, and that you make sure also of that. It's just a shortcut of the underlying rationality, because if it wasn't beautiful in this sense we now appreciate, we know already a priori that it is missing out a lot of the intelligences and performative capacities that this contemporary culture is offering us. So if this ended up just as a kind of modernist truss, we know it would be irrational with respect to the performance criteria. So the aesthetic values mean something. They guide us and summarize without every time having an intuitive, instant heuristics of rejection and searching. And that's a deep rationality of aesthetic sensibilities. And that's why the alignment of beauty, or that's the first important check. And it is beautiful. So then we have the chance at least to find a lot of these rationalities. There might still be a lot of things missed out and faults in it, but if it wasn't beautiful, we can forget it already. And that's the power of, let's say, aesthetic values. And how they become institutionalized in the contemporary as a guiding heuristics, and cannot be severed from rationality.